Welcome AP Physics Mechanics students. So I decided rather than posting a solution as a PDF file, a static document, I decided that it might be better for me to make yet another video of the solution to last night's homework, the AP Free Response Practice question FRQ short that was assigned yesterday, practicing how to answer a design your own experiment type AP question. And so the reason why is that now I could provide maybe a little bit of commentary so you could kind of see and understand my thoughts and the kinds of thoughts you should be having while solving a question like this. So let's begin first by me reading the question. So you got this diagram provided, and the question states, students are asked to perform an experiment to determine g, the acceleration due to gravity, which of course is 9.8. As an accepted value in the lab using the setup shown. They are expected to find g by plotting their data in a graph. I highlighted that because what a graph means is multiple trials. You have to be varying one quantity and seeing how that changes another quantity. So two x and y things that are varied, and then you see the shape of the plot. So that's the important thing. We can't just do one trial here. We have to make a procedure with multiple trials. The students have access to equipment commonly found in a high school physics laboratory, but the experiment must use the setup shown above, which includes a cart of mass m on a ramp, which is set at an angle theta to the horizontal. The cart is held on the ramp by a spring constant K. There is a negligible friction between the cart and the ramp. So what they're doing by giving you this setup is they're trying to lead you, or they are leading in the path of analyzing an inclined plane situation. Now, the mischievous part of me thought, well, I could get around that if I wanted to be a jokester by saying I could take, in my procedure, take the apparatus to the top of a building and drop it off the building and use the motion detector to plot the velocity versus time graph and take the slope, and that's g, right? I could have said that, and technically that's true, but I don't know if they would appreciate the humor in that. But what are they trying to do? Again, inclined plane. So this is the thinking that I went down. So you got to first imagine the force diagram. By the way, I just want to point out yet again an aside. If we were drawing this for credit, we would only draw the colored arrows. The gravity down, normal force, and then the spring force holding this from rolling down the hill. These components we use in our thinking to solve the problem. I sketched them in here. But if, again, this was for credit, I would not be able to draw those in. I'd lose credit. I could do that and draw components in a little mini diagram off to the side, but the part that I'm getting graded on, they won't take off for this off to the side, but if I put the components here, I do lose credit. So just be mindful that if you do have to draw a force diagram, I put these in here, but I don't want you to do that if it comes up on the AP and inclined problem. But anyway, so this y component of gravity, mg cos theta, cos because it's the adjacent side, adjacent the angle right here, that's going to be balanced out by the normal force preventing this mass from breaking through the board or the ramp. So, but that doesn't help us. What helps us is this part that normally creates acceleration down the ramp, mg sine theta, sine because it's the opposite side of the with the hypotenuse being here, mg. So mg sine theta, that has to be balanced by the spring force. Right here, spring pulling up. So this and this balance. So that's basically my expression where I'm going to have kx equaling mg sine theta. And now to make a graph out of that, I have x on this side, and on this side I could vary two possible things. The first solution I'm going to show you, I varied theta. The bigger theta got, the bigger this got, and therefore the bigger this got. So I would have x on the vertical axis and sine theta on the bottom axis. You'll see that coming up. The other possibility is I could keep theta of the ramp constant and I could vary the mass of the cart by stacking more blocks on the top of this cart over here. And that would make this bigger and therefore X bigger, and I could also generate a graph that way. So that's the thinking, what they're trying to lead me down. I have to get that in my mind before I even start thinking about a procedure. What is the physics here? And I don't have to work out the details yet, but I kind of have to know where I'm going. And that's what I'm going to do. I'm going to vary theta, make the hill steeper and steeper, and measure X as a result. Okay? So let's take a look at my actual solution. That, again, those were just thoughts. First, let me just show you this. So this year on the AP, you know, you're doing it online. And notice I typed some things and then I wrote out other things. My point being, at this point, just a little strategy. Look quickly and decide. Sometimes it's nice and convenient to type. Well, personally, I type faster than I write. If that's you, you type faster, type out any kind of parts that you can answer with text. But then it came to some calculations. This would be very awkward to do in a word processor. So I write it out on a piece of paper. Have a stack of blank paper next to you when you take the test. Jot down and write this out this really quickly, and then snap a picture and load that as your answer. So again, pick whatever is going to be most convenient to answer each separate part. Okay? All right, so that's just a little something. So let's now go ahead and think of our procedure. So part A says, let me just do this. Okay. Briefly identify each quantity to be measured, the symbol used to represent that quantity, and the equipment that would be used to measure the quantity. So the first thing, again, as I mentioned, when you answer these, you have to not just say measure the mass. Right? That's what we would say if we were just talking in class. Oh, go measure the mass. And everyone would know what you're talking about, right? But in these questions, you have to say, okay, I got to use the electronic balance to measure the mass. Not a stopwatch, obviously. Everyone knows that, but you got to say it. And nonetheless, that's part of the question, part of the grading schemes. If you read there, it says that. And then also, you have to give the little symbol, mass M, measure the mass M. So 3 things for every measurement. What you use, what it is you're measuring in words, and then the symbol you're going to use. By the way, you know, this kind of, you know, when I read this, I was like, well, they already did that for you, right? They said mass M, right? But again, it tells you here to do it again, so it's a bit redundant. Go ahead and make them happy, say the 3 things. Here, use the protractor to measure the angle of the ramp. Protractor, measure angle, ramp Q. And by the way, because I'm using a word processor, the word theta, the symbol theta would be very time consuming to put in. In the part before here, there was a little paragraph I cut out just for sake of quickness. They said if you wanted to, you could use some other symbols that were more convenient as you're typing your solution out. So they mentioned you could say theta would be Q instead. So that's what I'm going to do as I'm typing. Next thing, use a meter stick to measure Li, length initial, without the load, the spring length, and measure the spring length L final with the load to determine spring displacement X. So you see meter stick, what I'm measuring, spring lengths, the symbols, and displacement symbol. So again, 3 things for each measurement. All right, so let's move on to part B. Briefly describe the procedure to be used to determine the acceleration due to gravity. Provide enough details so that another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use symbols defined in part A. Okay, so I wrote first step, using the electronic balance, mask the cart. And notice I left some things out here. I did this on purpose because when I went back and looked, I said, you know what, I didn't do the 3 things again. And so I left that as an example to you. So I use electronic balance, right? And then I'm measuring the mass of the cart, but I didn't reuse the symbol M. So let's see. As symbol, use the symbol. So I probably would have lost credit there. So I should have said measure the cart of mass of the cart M. Okay. So now, if I didn't put this electronic balance here, I'm not sure I would lose points because I already said electronic balance here. But in here, they explicitly said that as needed, use the symbols defined in part A. I didn't use that symbol. I would have lost points there for sure. If I left this out, well, it's questionable. Maybe I wouldn't have lost because I already stated that up here and it didn't state it again in part B. So here I was better using the meter stick to measure the length of the spring Li without a load on it. So the three things. But again, like I said, maybe this is not necessary in this part because I set it up here. Set the ramp up at a small incline of approximately 5 degrees. Okay, so I do that and use the protractor to measure precise angle Q, okay, which I meant to be theta. Put the car on the spring and allow it to rest at equilibrium. Measure L final of the spring and record it as X equals L final minus L initial. So that's now I have an X and I have a theta for that particular incline. Next step, increase the incline by approximately 5-degree increments. Each time use the protractor to measure the precise angle. Then use the meter stick to determine L final and the X by that formula every time until you reach an incline of about 85 degrees. So I'm going to have, 8, 9 data points, as I keep increasing that angle, I am going to make a bigger angle and a bigger spring displacement. Bigger angles, bigger spring displacement. So there's my procedure. I think with the exception of that little M symbol, I think it's more or less complete. All right, part C. Which quantities that were measured in part B would be graphed in the horizontal vertical axis to produce a graph that would be used to determine acceleration due to gravity? So I said I would plot sine theta on the horizontal axis and X on the vertical axis. If I did X versus theta, as I already mentioned, I would get a sine graph like this, and we'll see that in this next part, Y. And then, so what I'm going to do is put X versus sine theta like that, and that will give me my straight line. So now, how did I know that? Well, coming from part B, it says describe what information from the graph described in part C would be used and how it would be used to determine the acceleration due to gravity. So what I have to state is I would draw in that graph that I mentioned with the axis set up as with sine theta on the horizontal and X on the vertical. I would draw a best fit line and then calculate its slope. Okay, then what does that slope tell me? Well, here is what the slope tells me. I say, again, the spring force up the hill is balanced by the gravity X component down the hill, right here. And then I solve for X on this side, and I leave sine theta by itself, and all the terms in the front I gather here. Now I have the equation of a straight line. This is on the y-axis, this whole thing is on the x-axis, therefore this is the slope of my graph. So slope is mg over k, and therefore if I solve this for g, I would take the slope and multiply by k, and then divide by the mass, and there would be the acceleration due to gravity. So there is part D, describe, right? I'm showing, and I'm not calculating, right? I don't know what it is because I never did the experiment, but I certainly am describing how I would get it. Okay, so that's part D. All right, moving on. Okay, part E. Oh, let me show you part E. Okay. So, part E. In a second experiment, student place a different cart of unknown mass on the ramp and attach it to the spring, letting the cart and spring come to rest. The cart is then displaced slightly down the ramp and released, causing the cart to oscillate on the ramp. The student creates the position versus time graph shown above using a motion sensor. Briefly describe how the students could use the graph to determine the mass on the new cart. So you put the cart here and then you pull this down or push it up and you let it go and it's going to oscillate like this, right? So that's what this is showing. It's decreasing in amplitude because of friction, by the way, but that's not necessary to answer the question. So how would I answer this? Well, I chose to write this in the word processor because, again, I'm writing a lot of words. So it's a little awkward with the equation, but I would use the expression T equals 2 pi square root of m over k. And the fact that the period t is approximately 1 second from the graph, right? It goes through one cosine function in 1 second, then another one in another second. So every second it goes through a cycle. So I know the period is 1 second from the graph. I would substitute this and the known spring constant K, because they said the spring constant was known, and then solve for M. All right, so I plug in this, K would be known, and I'd solve for M. So again, I'm just describing, briefly describing. I'm not actually solving because I don't have any numbers. So again, you see, this would have been easier if I could write it out with a pencil, but once I started typing, I decided to stick with the awkward writing equations in Word. Okay, so that's acceptable, especially this year. So that's one possibility. As I said, I varied theta, and I saw its effect on X. But as I said also, you could also vary the mass and see its effect on X. So that's the next possible solution that I'm going to show you. And the reason why I'm showing you two solutions is because these design your own experiment questions are open-ended. So you can think of multiple different kinds of procedures, like the two I mentioned with the incline, and the third one I mentioned in the beginning, right? Throw it off a building, and that could determine G technically with a graph too. You could come up with, I'm sure, even more different possibilities. So again, this is just to show you that there is another possibility. So as I mentioned, this is the thinking I would do before I solve the problem. I'd do the same thinking about the forces balancing, and then I would say, okay, I'm going to vary mass M. That's going to be on my horizontal axis, and this is going to be on my vertical. So this is like y equals mx plus b. This would be my slope, right? So that's the thinking that I have to do, and now I could come up with a procedure. So here you see I use an electron balance to measure M, protractor to measure the angle, and then the spring lengths. So this is all the same as before, so I don't need to go into too much detail. But this is a little bit different. So I use the electronic balance, mass Descartes. Again, I should have said mass Descartes, mass M, right? So they mentioned that I had to put symbols in there. Use the meter stick to measure the lengths without a load, and then set up an ramp at a substantial incline of 30 degrees greater. Remember they said that you have to have a procedure that minimizes the error. If you have a very small incline, there won't be much gravity component and the spring won't stretch by much. And when things don't move by much, the displacement will have a lot of random error in it. So I want a good healthy spring displacement. So I want the incline to be reasonably high so that it really does stretch the spring. So that's me attempting to minimize the error. So the other one, when I went slowly, it takes care of that because I go through the whole range of theta, so the trend would, you know, the smaller incline would be seen within a larger trend. But if I do the whole experiment with a small incline, it's not going to be very accurate. So there's that. Okay, use the protractor to measure the angle Q. Again, I'm saying what I'm using to measure. Then I put the cart on the spring and allow it to rest at equilibrium. I measure the final spring length and then record the spring displacement as the difference between the two spring lengths. So far I'm the same. But here's the difference. Using the mass set, a mass set, because they said you have, you know, the equipment that's generally available in the science lab, in a physics lab. We do have mass sets in a physics lab. Add a known mass to the cart. Record the total mass of the cart M, cart mass plus the added mass. So like in other words, if this is 2 kilograms and then you put 0.5 kilograms on top of it, it's 2 and 0.5 or 2.5, right? So that's the total mass. Use the meter stick to measure the new equilibrium length, L final, and record this new displacement. And then the last step, repeat until you have 8 total data points of X and M. Now, what am I plotting on the graph? I would plot M on the horizontal because that's the independent variable. That's what I have control of. I'm stacking more mass on the car, and then as a result, we get a certain spring displacement. So that's on the dependent variable, the y-axis. So there, that's what I put. Mass here, and then X on the vertical. Maybe I slipped that in here so you could see it. So M here and X, and that would give me a straight line. So then part D, if you remember, it said, okay, describe what information from the graph described in part C would be used to, and how it would be used to determine the acceleration due to gravity. So once again, I've got to come up with some kind of linear trend and see the significance of the slope. So same thing, the spring is balanced by the, is balancing the x component of gravity. This time I slip the m to the side, that's my independent variable, and then I solve for x, that's my dependent variable, and I lump everything else together in front here. This is now y equals mx plus b, a straight line where this is the slope, right? So now again, I'm solving for g. So I calculated my slope of my best fit line, I plug in that number here, and then I solve for g by bringing k over and then dividing by sine theta. So there's a description of how I would get g from this graph over here, okay? Now part E is the same. It's no different. It's the same question, so I won't go over that again. So there it is, a brief presentation of two different solutions to that free response problem, how to design your own experiment. So hopefully you caught all the things. You know the three ways you have to refer to the data. You know what you're using to measure, what you're measuring, the symbol, and then a little bit about how you come up with thinking and a procedure, and then also how you can use a linearized graph to figure out what the slope of the graph is going to be in terms of the variables in the experiment. Okay, so probably the last video before the test. So I wish everyone luck, and I hope everyone gets a 5 out of 5, and then we'll all be happy and we could celebrate. Well, we won't find out till summer, but nonetheless, it would be a great achievement to a very productive year, and a great year. And again, I wish you well.